Great. So, hello everybody, and welcome to this presentation, Understanding Topography, an Introduction to Topography. My name is Markus, and I've been working for Swisslens for over 17 years now, customer service, product management, colored lenses, and topography. I'd like to start with a question for you. What are the different maps for? And I mean these different charts, plans, or let's call them maps, like axial, tangential, elevation map, and many more. Finally, every map gives us different information. And I like to compare it with maps you know quite well from geography in school, talking about countries and continents. There are also different maps like population, topography showing mountains and flatland, and agriculture products, even temperature maps, whatever you want. And putting all into one map will not work. You will not find any information. So that's why you need different maps. Each of them gives you another information. And it's the same for the topography of the cornea. It depends on the information that you want to have, which map you choose. And sure, you don't need for every fitting and every examination anytime all maps. Now I'd like to start with one of these maps, and it's the axial map that is also called sagittal map for some devices. But it's the same, axial map is equal to sagittal map. This map gives you information about the vision, all that has to do with the vision, power, quality of vision, refractive changes caused by autokeratology or medical treatment like LASIK. This map is reliable in the center but less precise in the periphery. But as vision is important in the center, in the area of the pupil, and not in the periphery, that causes no problem. And when this map is shown in curvature in millimeters as unit, it is also used to calculate the base curve of contact lenses. And last but not least, you can see if an eye has an apical or limbus to limbus astigmatism. That's important to know if the fitting will be easy or more challenging. Above, you see an example of an apical astigmatism that is mainly happening in the center. You can see the difference, K steep, K flat, but in the periphery, you have only 16 microns difference. You can see it also in the area of the white ring that I've marked here. You can see more or less around there's one color, so quite spheric. A spheric lens would work very well. In comparison, below, you have 38 micron as difference in the periphery. So the astigmatism is running from limbus to limbus over the whole cornea. A toric back surface will be necessary here. So even if we have the same difference in the center, here 0.26, 0.28, the periphery is very different, and that's important for the fitting. In comparison to this axial map on the top, the tangential map shows us the shape, the form of the cornea. It can show you better, fine details, and gives more realistic data for the periphery of the cornea. Thus, the bullseye of auto-K treatment is controlled with this map. We will see examples for that later, but for now, keep in mind the axial map for the vision and tangential for the shape. There is a third important map I like to present to you, and it's the elevation map. Sure, there are much more maps, but in my opinion, For contact lens fitting, you can do almost everything with these three maps. Be careful when it comes to heights. That's what the elevation map shows because there are two ways or two maps for the height. One is the absolute height, the other one is the relative height, quite often called elevation map. For the absolute value, the height is measured against the plane surface, which makes it difficult to find small differences in height. Be careful for most applications. The relative view here on the right side, where the height is measured against the curve called reference sphere, will be much better and more practical. You can see details much better. There are a lot of things that you can do with this elevation map. But finally, what does it show? On the right side, you can see this image showing a thin green line representing the reference sphere and a fat line in black for the cornea. Every part of the eye that is in front of this reference sphere has a positive here red value. The one behind the sphere a negative blue value. Every fluo image simulation that you are doing is based on heights. The dark or even black areas showing very small differences between the back surface of the lens and the cornea means small differences in heights, whereas the bright green areas show pooling, so a lot of through high differences. Furthermore, this map can give you an information where the lens might later decenter to. Normally, a lens will drift to the negative part of the elevation map, the one that is behind the reference sphere. So in this case, there might be a tendency of the lens to decenter downward. Then there's an interesting study and a rule how to decide if the fitting of an RGP lens or a sclera lens will be easier to manage on a specific eye. This can be helpful for an irregular cornea. For this evaluation, you just have to take the difference of the maximum and the minimum height, means the most positive value minus the most negative value, like in this example here, showing plus 170 as highest value, and here minus 175 micron as lowest value. So a difference of 345 micron. And the rule says that if you have under 350 micron, an RGP lens would have a success of 88% success in the fitting, and that has been taken as a limit or as a threshold. When you are over this value, over 350 micron, in the difference of the height, it's getting more difficult with a RGP lens, and the sclera lens might be the better choice. But in this case, in this example with 345, an RGP lens should still work quite well. And just to mention it, this elevation map can also show you the position of the apex of verticonus quite well and other things, but that no longer fits in the 25 minutes that I have. So we were moving on to autokeratology and the maps that you can or should use for it. Normally for autokeratology, the differential or subtractive view is used. And what does it? It compares the cornea before starting with AutoK, so the first initial measurement, with the cornea after wearing the AutoK lens. And thus it shows us just the changes that were happening. So the difference of both images. On the left side above, you see the first measurement. On that base, the lens is constructed and produced. The examination B below is after the lens is worn. On the right side, you see the changes, the difference, examination B minus A. Here we use the axial power map that shows us the vision. And you can already see how much power we have modulated. It's already shown here because it's the difference between these two topographies. It's minus 3.9 diopters. So the myopia is reduced by minus 3.9 diopters. You can also see the flat blue treatment zone here and its position compared to the pupil, the black ring. Now we have changed to the tangential power map that shows us the shape. And what we see here is the famous bull's eye, the red ring that shows the steepening in the periphery, the reverse curve of the modulated cornea caused by auto-K treatment. This shows us the centration of the lens during the night. On that base, we can decide if the centration is already good enough or if we have to change something concerning the fitting of the lens. If there's a high riding lens causing a smiley face or frowny face, a lateral decentration, or whatever. Now I'd like to ask you if this auto-K lens is centered or decentered during the night. Be careful at this is the axial map now, and you might say that the lens is decentered. But if you compare it and we change to the tangential map on the right side, you see a well-centered bull's eye. So finally, a good centration of the lens during the night. Normally, for a modification or an advice, you would always need the first topography and the last one that you have taken. But if you can't send us all topos, all informations, the first measurement and the final, please send us this subtractive or differential tangential power map. It will give us always the best information. This differential map can show all changes of the cornea, not only caused by auto-K. For example, here it shows us the difference of the cornea just after taking a daily multifocal lens out of the eye and the next day. And you can see in this comparison map how the cornea was molded by wearing the lens and how it starts now to relax or to rebuild. You see the flattened zone here in blue, and then a red ring, and so on, the steeper, flatter areas. Again, you just see the topography of a cornea, not over the lens. Here are the two images. You can see here the two images that were compared. And in the cross section, that's very important and interesting to see. You can see very well the wave is going up and down with the power. You can see the line here. That's exactly what you're seeing here. And it might be a lens design, like in this picture, with different concentric zones for distance and near vision. Well, sure, not the best fitting in this case. With a differential map, you can also see quite well the progression of keratoconus. In this example, the topographies from 2008 and 2011 are compared, and you see a progress of 3 diopters over the time on the apex. So as you have seen, you can do a lot with this differential subtractive map. When we talk about topography, the quality of tear film and the influence on the topography is very important. It's a well-known topic in theory, but often ignored in practice. But the influence of the tear film on the outcome of topography is a very important fact. And that counts for every topographer that is based on reflection, means mainly Placido ring systems. So the quality of the tear film, like a local breakup of the tear film, will influence the topography. like the sim-k radius in the center, the eccentricity, or generally the transition of the colors that are shown on the topography image. If you take a look at these 4 topographies that were made from the same eye, so just within a minute, more or less at the same time, and I ask you, do they all look the same? Number 1, 2, 3, 4. You may have noticed that for image number 3, there is something spooky with this red area here. Maybe it looks like a conus, but what was happening there? And which one is the right one? Which one is correct? Here you see the reflection of the Placido rings of this topography number 3. And within these red circles, you can see that some rings are distorted, not homogeneous, not sharp, and that represents problems of the tear film. So you can't trust the topography, it will not be reliable. So tear film affects topography. I show you 2 examples. One of the left side here, a good topography, on the right one with the bad one. Just compare the rings. Especially here in this small picture, you see these distorted rings floating one into another. How to make it better? How to avoid these problems? And I like to recommend you, let the patient blink and then ask to open his eye wide. When you're then taking the topography, it will give you a very good tear film and a large coverage of the cornea. There is an interesting study about blinking and the quality of the tear film, and it found out that the best stability of the tear film is between 1 and 4 seconds after blinking. So try to catch this moment, because the tear film needs about 1 second to stabilize after blinking, then it's stable, and after that the thinning starts, leads finally to the breakup. Some devices, like the Medmont Meridia, even offer a much more understandable colored map for this. So you don't have to search for distorted rings in the picture. Here's a colored interpretation of that. And if everything is in blue, that means a stable, good, uniform tear film. Green or even red areas are called dry spots, hot spots, and are showing a thinning or even a local breakup of the tear film. Ensure of the patient to open his eye as large as possible to catch a large surface of the cornea. Also here, a very good example on the left side, a bad one on the right side, where the upper eyelid covers too much of the cornea. I'd like to show you another example. We have again 4 measurements. Which one do you take? Difficult to say, but however, we see quite harmonic transition of the colors in picture number 3. The others show slightly red centers or areas, as you can see here in number 1, or here in number 2, or number 4. And they are they don't look always the same. They are at another position, and that is typical for problems coming from the tear film. If this red area will always at the same position, we can be sure that it's coming from the cornea. But to be sure, let's take a look at the tear film. Switching to the tear film quality map, I think it might be already easy for you to find the best one. You see a lot of blue, quite uniform in picture number 3 compared to the others. So be careful if measurement look different on the cornea. It seems when the cornea seems irregular, it's maybe only a problem coming from a bad tear film. So as you have seen, Topography is more than just pushing the button, and note topography is the basis for a successful contact lens fitting. In summary, understanding topography allows you to interpret or understand the real shape of the cornea and what problems may arise and how to avoid them and how to make it better. Um, Finally, you will have more fun and more success in fitting contact lenses. Another important point about the quality of topography, apart from the tear film, is the type of construction of the topographer. Now I like to compare two different topographers that exist on the market. One with a large cone for measurement, you see it here, and on the right side, the Medmont Mevidia here with a small cone for the measurement. Both topographies were made from the same eye, and sure, they are scaled, so both sizes are the same. With a large cone topographer, you can get a capture of maybe 8 millimeters, vertical even less, compared with over 12 millimeters, or even more on the right side for the Medmont Meridia. But it's even better to compare the advantage of the size when I take the measurement of the area on the left side, make it in white, and just put it here in this right image. Now, all colored areas you can see around this white spot is additional data that can be measured with Medmont. What's your advantage for the fitting? Well, let's just put a normal RGP lens with diameter 9.8 on this eye. And what you can see that quite a large part or area of the contact lens is not covered by the topography of the large cone. The white zone here you can see is not measured, whereas the small cone gives far beyond the lens if you see well colored here. And for larger contact lenses like auto-K lens, the difference is becoming even bigger, as an auto-K lens has only contact with the cornea with its alignment zone in the periphery, here shown with this gray ring. You can see that on the left side, almost no measured data for the large cone that reaches or covers this alignment zone of the contact lens. Also here, the small cone gives us much more data going far over the lens. So the topography should cover the lens diameter. And such a high quality topography allows you to build a perfect lens. You can compare the simulation, the real fluo image, and the bullseye of the topography, and especially here in the cross section, the simulation and the real topography show more or less the same result. The same for a multi-curve lens, slightly touching here and here in the periphery, and the same in the simulation on the right side. And more fluo here in the center. It's well comparable for both images. And here for a keratocone, slightly bearing contact here and here. And you find the same in the simulation. And here in the middle, you can see a lot of fluorescein. Also, here in the fluo image simulation, it shows really the same. So in summary, with such a high quality topography covering the whole cornea, in the simulation tool, you will get a much higher rate of success with the first lens. Okay, a small commercial break. In the end, I would like to give you a short overview of the Medmont Merida topographer. Medmont has already more than 20 years experience in topography, and maybe you know the legendary E300. The Merida is a follower, the newer one, about 4 years on the market now. The Medmont Merida is more than just a topographer. But sure, the biggest advantage is this large limbus to limbus topography. Then you have an incredible high resolution camera system um, that allows you to take images and videos with fluorescein and with white light. So you have a full documentation of the fitting that can also be easily exported and shared with a customer service team of your contact lens company if you need support. Then you have mybography with infrared light, the contact lens fitting software that I've already mentioned. And there are several functions for the dry eye, like tear film breakup time, ratings for red eye, staining, ensure the mybography, and you can put all into one complete dry eye report. What you can see here is a picture made with a zoom function of the Meridia Pro model. Look how sharp it is. Can your slit lamp do it better? Here you see a video with white light for controlling the centration and movement of the contact lens. Look how evenly and uniform the lighting illuminates the whole eye, no shadows or poorly illuminated areas. Look at the eyelashes, very sharp also. And you have the same possibility, of course, with fluorescent images with blue light. Record your examination on video and share it with us if you need support or just for your own documentation. Well, if some of the things that I mentioned or tried to explain about topography seems maybe too complicated or you're not sure about a fitting, what to do, that's no problem because Medmont makes it very easy to export and share the data with any contact lens producer. And there is a direct interface, a Swisslens button, that allows you to send topographies directly from the Medmont software to us. Or you can export the data and then sending that file to every other company, but sure, favored to Swisslens. You can even create a PDF or JPEG, whatever you want. So many thanks for your attention. We are at the end. I hope that you enjoyed the presentation. I hope you learned something new, or at least some things about topography are more clearer now for you. However, thanks a lot for your participation.